There is nothing that requires attention tonight. No sequence to follow, no test at the end, no conclusion to hold on to. What follows is simply an examination, one material taken slowly, studied in genuine detail, with nowhere in particular to be. Some people arrive at this kind of content after a day that asked too much, looking for something that asks nothing back. Others come because a subject taken apart carefully, with real patience, has its own particular quality of stillness. Not because it is simple, but because specificity, offered without urgency, tends to quiet something that generalities rarely reach. Neither approach requires full attention. What follows holds just as well at the edge of sleep as it does with eyes open in a lit room. The material does not need to be followed closely. It simply needs somewhere to be. There is a kind of curiosity, patient, unhurried, that does not need information to arrive quickly to find it satisfying. That kind tends to appreciate a detail for what it is, rather than for where it leads. This is the kind of content built for exactly that quality. The facts here are not racing toward a conclusion. They are settling, one at a time, the way sediment settles in undisturbed water. Before we start, subscribing to the channel and liking this video will help more people discover this content. There is a room, a real kind of room. The type found in older buildings attached to working apiaries, or in the back corridors of natural history collections that have been accumulating things since before electricity, where sealed glass jars line wooden shelving from floor to ceiling. The light in these rooms tends to be low. A soft, amber-tinted light fills the room, and with it a quiet arrangement of scents. There is beeswax, and beneath that, aged timber, and beneath that, something mineral and difficult to place, a faint sweetness that has spent years settling out of sealed glass until it became the very air of the room. If I'm being honest, a room like this would be enough to make me sit down and never quite manage to leave. The jars do not all look the same. Some hold a pale, almost water-clear gold, nearly translucent in good light, the color of late afternoon sun through thin curtain fabric. Others sit in deep amber, close to opaque, their contents almost burgundy at the center where the glass is thickest. A few have begun to cloud from the inside, the material shifting from liquid toward something slower and more crystalline, the internal chemistry moving at the pace of weeks toward a more ordered arrangement. There is no urgency in any of it. The jars are not going anywhere. What they contain is, by any reasonable measure, in no particular hurry. A room like this tends to make the air feel slightly thicker, not unpleasantly, but perceptibly, as if the density of what is stored has communicated itself outward to the space it occupies. The shelves do not creak, the jars do not move. The only sound on most evenings is the soft, particular absence of sound that belongs to rooms full of sealed things. What sits on those shelves is one of the most chemically complex edible substances that exists on Earth, not in a general or approximate sense, but in a measurable one. More than 600 distinct flavor compounds have been identified in honey so far, and the work of cataloging them is not finished. That figure does not include the structural sugars, the enzymes, the organic acids, or the trace minerals that make up its chemistry. It is simply the flavor profile counted on its own. The full picture is considerably larger. The color of honey, the quality that stops the eye first before anything else, is not cosmetic. It is information. Color in honey corresponds directly to the flower sources the bees visited and to the mineral content of the nectar those flowers produced. Lighter honeys tend to come from acacia, clover, or orange blossom, sources with lower mineral density and specific sugar ratios that scatter light rather than absorbing it. The color in formal measurement is classified on the Pfund scale, which runs from water white at the pale end, graded from near zero, to dark amber above 114 millimeters. The number describes how much light the honey absorbs, which is, in practical terms, a measure of how much the honey contains. The jar that appears palest is not the simplest. It is the most transparent about its composition. Held up against a lamp in that kind of room, a jar of pale honey behaves almost like a lens. It bends light gently, concentrating it into a warm pool at the far side of the glass, the same effect in principle that makes the bottom of a swimming pool appear closer than it is. This is the result of honey's refractive index, which sits between 1.484 and 1.504, depending on water content and sugar concentration. That number is not fixed. Refractive index is simply the degree to which a material redirects light passing through it, a property that changes measurably as the internal chemistry of the honey shifts. A jar of fresh honey and a jar of the same honey 6 months later will bend light at slightly different angles because the material inside has continued, very slowly, to change. The weight of a full jar, picked up without preparation, tends to register as more than expected. Honey is considerably denser than water, approximately 1.4 grams per cubic centimeter, which means a liter of it weighs around 1,400 grams, roughly 40% more than the same volume of water. The density comes from the sugar concentration, a large proportion of fructose and glucose dissolved in a relatively small amount of water, pressed together into a liquid that has a compact in a way that does not immediately show on the surface. The weight announces itself before the eye has had time to form an estimate. There is something in that recalibration, the jar heavier than expected, the hand adjusting, that is specific to dense, patient materials. Honey has the weight of something that took its time. The surface of honey held in a shallow container has a visual quality that resists easy description. It does not settle flat in the way that water does. It holds a slight dome, a gentle convexity at the center, a slow refusal to become perfectly level. This is the viscosity at work, honey's reluctance to spread, to release its own weight without considerable deliberation. At room temperature, honey's viscosity runs between approximately 2,000 and 10,000 centipoise, depending on its sugar ratio and water content. Water, for comparison, measures 1 centipoise. Honey is, by that measure, somewhere between 2,000 and 10,000 times less willing to move than water. That is not a poetic exaggeration. It is a ratio arrived at by measurement. Pour honey slowly from its jar. Hold it at a height above a bowl and watch. And what you notice first is simply how long it takes to arrive. It is dense enough that the descending thread seems genuinely reluctant to leave the glass, as though it had been perfectly comfortable where it was and sees no reason to be elsewhere. There is something almost like a newly woken creature in the way it moves, slow and unbothered, as if being poured at all was an inconvenience it has not yet fully accepted. This behavior is a consequence of the molecular structure of the sugars inside. Those molecules are not simply floating in solution. They are interlocked at a density that gives the liquid a kind of structural stubbornness, a measurable resistance to changing its own geometry, even while technically in motion. The fold is not random. It is the natural expression of a material that is, at any given moment, on the verge of becoming something even stiller. Suppose the smooth, inviting surface of honey catches your attention and you press a fingertip into it. What you find is a substance with no real interest in letting go. Draw your finger back and the honey follows, stretching outward in a slow, narrowing thread rather than releasing cleanly. It thins and thins further, and eventually concedes, though only after considerable resistance. Whatever surface the honey was resting on will, in all likelihood, bear the quiet evidence of that parting. This behavior has a formal name, viscoelasticity, which describes the property of a material that behaves simultaneously like a liquid and like a slow, compliant solid. But the everyday experience of it needs no formal name to be recognized. The thread is the evidence. The material is holding itself together while still technically flowing. The color of honey deepens even inside a sealed jar over time. This is a real chemical process, a slow reaction between amino acids and reducing sugars called the Maillard reaction, which is the same process responsible for the brown crust on baked bread, the color of caramelized onions after a long, patient heat. In honey, the reaction proceeds without any external heat source, driven entirely by the natural chemistry already present, at the pace of months and years rather than minutes. A jar of pale clover honey kept at room temperature for several years will be measurably darker than it was when sealed. The color is a record of time. It is visible, and it is honest. There is a further detail here that tends to go unnoticed. The same variety of honey from the same apiary will shift in color between seasons as the composition of the bee's foraging changes. Spring honey and autumn honey, produced by the same hives in the same location, can differ by several Pfund grades as the late-season flower sources, with their different mineral profiles, replace the earlier ones. The jar does not tell you the year, it tells you the season and the landscape, and something about what was flowering in the weeks before it was sealed. What the eye cannot immediately see, what requires a different kind of attention or a different instrument, is that inside every jar of honey at room temperature, the glucose is very slowly reorganizing, finding at the pace of cold chemistry the crystalline geometry that will eventually hold it still. A jar of honey left behind in the refrigerator, forgotten, comfortable in its own quiet corner, will, over time, begin to change. The color shifts toward a pale, clouded tone, as though someone had stirred a little milk into it and left it to set. The texture thickens and firms, and if you look closely, you can make out the fine, granular accumulation of sugar crystals gathering within, visible, unhurried, and entirely indifferent to being observed. I know this not from reading about it, but from leaving a jar too long and coming back to find it had rearranged itself in my absence. That slow consideration, the glucose finding its preferred arrangement, is not something the eye catches first. It is something the hand notices. Before a jar of honey shows any visible change at the surface, before the clarity shifts or the color alters, the texture at the base of the jar has already begun to feel different. A slight resistance, a faint, almost imperceptible graininess that was not there the month before. The hand is, in this case, a more sensitive instrument than the eye. It reads the material's interior decisions before they have finished expressing themselves outward. Honey held in the palm does not warm quickly. This is one of its less obvious tactile qualities and one of the more interesting ones. Most liquids at room temperature will begin to absorb the warmth from a hand within a few seconds, adjusting toward body temperature fairly quickly. Honey does not. Its thermal conductivity, the rate at which it accepts or transfers heat, is low enough that a spoonful of it held against the skin stays at its own temperature for a noticeable period before the warmth begins to penetrate. Unlike most liquids, honey does not readily accept the warmth of a hand. It is, in a sense, the opposite of a chameleon. Where a chameleon adapts instantly to its surroundings, honey seems to say, "Nothing around me is of particular concern. I remain exactly as I am." The resistance of honey to being stirred has a specific character. Move the spoon at a slow, steady pace, and the honey draws around it with a deliberate, even weight, a consistent drag that does not hurry to accommodate the movement. Increase the rate of stirring to a continuous, moderate rhythm, and the same honey yields more readily, thinning slightly in response to the sustained agitation, flowing with less effort around the implement than it offered at rest. This behavior, the tendency of certain fluids to become less viscous under sustained shear force, is called shear-thinning. Honey is a shear-thinning fluid. Its viscosity decreases as the rate of stirring increases and recovers gradually when the stirring stops. The material is not stubborn in the way a paste is stubborn. It adjusts slowly to the pace imposed on it. The temperature of honey at the time it is handled changes its tactile character completely. In the cold, honey gives every impression of having decided it is perfectly comfortable where it is and has no intention of going anywhere. Press a spoon into it and the honey resists as though it were a day of rest and the spoon an unwelcome interruption it has already made up its mind to ignore. At 35 degrees, the temperature of a warm kitchen, or a human hand held around the jar for several minutes, the same honey flows freely, thinning toward a texture closer to a heavy syrup, responsive to the slightest tilt of the container. The same material, a difference of 20 degrees, two entirely different physical experiences. This temperature sensitivity is connected to the behavior of honey's primary sugars. Glucose, which makes up roughly 31% of honey by weight, responds strongly to temperature. At lower temperatures, its molecules slow, begin to cluster, and seek out their preferred crystalline arrangement. Fructose, which sits at approximately 38.5%, is considerably more reluctant to crystallize, and at lower temperatures simply becomes more viscous without organizing into solid form. The two sugars coexist in the same jar, responding differently to the same conditions, one drawing toward order, one resisting it, and the balance between them is what determines whether a jar of honey sets firm, sets partially, or remains liquid indefinitely. The texture of fully crystallized honey against the finger is one of the most specific tactile sensations that honey offers. The crystals are not sharp. They have none of the angular quality of table salt or sugar held between the fingers. The individual glucose crystals in set honey are fine enough and are suspended densely enough in the remaining liquid that the texture reads as a smooth, fine-grained resistance, closer to the feel of very cold butter than to anything granular. Running a thumb across the surface of set honey in a jar leaves a clear path that holds its shape, the walls of the channel remaining clean and defined rather than collapsing back as liquid honey would. The material remembers the pressure. It keeps the record of it. What is happening inside that texture at a scale below the fingertips' resolution is that individual glucose molecules have arranged themselves into a repeating lattice, a geometric pattern that locks each molecule into a specific position relative to its neighbors. The way a room full of identically shaped furniture can only be arranged in a limited number of configurations before the geometry of the pieces dictates the outcome. The crystal does not form randomly. It forms precisely, each unit extending the pattern of the one before it, building outward in all directions from a single starting point, often a pollen grain, a tiny air bubble, or a microscopic particle of existing crystal that acted as a template. That starting point is called a nucleation site. It is the place where the patience of the glucose finally arrived at a decision. There is a further tactile quality to honey that is easy to overlook because it is subtle. The way the material clings differently on different surfaces. On glass, honey releases cleanly given enough time. Gravity eventually wins, and the jar drains with patience. On wood, honey tends to hold longer, the slight surface roughness of the grain giving the viscous liquid more to grip. On metal, particularly cold metal, honey releases quickly, the low surface energy of a smooth, cold surface offering less purchase to the molecular adhesion that makes honey prefer to stay where it is. None of these differences are large, but they are real and they are consistent, and a person who works with honey regularly learns to read the surface before the pour. When honey first meets the tongue, what arrives is not sweetness. The weight comes first. Honey is dense, and the tongue registers that immediately. The warmth follows, slowly. The sweetness comes last. This is the density again, the same 1.4 grams per cubic centimeter that surprises the hand when it lifts the jar. but experienced at a scale where the nervous system is considerably more sensitive. The weight arrives first. The warmth follows as the body temperature begins to move through the material. The sweetness comes last as the enzymes in saliva begin to work on the sugars and the first molecular transformations begin. The temperature sensation when honey meets the tongue is specific. It arrives slightly cool, cooler than the mouth, and then transitions over several seconds as the honey warms to body temperature. This transition is slow enough to be perceptible as a distinct experience, a period of coolness, and then a gradual warming, and then an equalization. The slowness is the thermal conductivity at work again. Honey accepts warmth at its own pace and communicates that pace clearly to anything in contact with it. Beneath that surface quality lies something that is easier to feel than to see, the particular way honey resists separation. When a finger is pressed into honey and slowly withdrawn, the honey does not release cleanly. It extends, drawing upward in a thin thread that narrows and narrows before finally giving way, the break point arriving later than with almost any other common liquid. This behavior, the extended thread, the reluctant parting, is a direct expression of the molecular cohesion between the sugar chains inside the honey. Those chains have a preference for staying connected. The thread is not a surface tension effect, as it would be with water. It is the interior structure of the material, communicating its own architecture through the fingertip. Set alongside that resistance is something less visible, but equally present. The way honey at room temperature moves in response to prolonged, gentle pressure rather than immediate force. If a sealed jar is tilted slowly and held at an angle, the honey shifts, but the shift takes time. The material flows, but it flows on its own schedule. The mass at the bottom of the jar takes several seconds to begin migrating toward the lower edge, and it does so with the deliberate quality of something that has decided to move, rather than something that is simply falling. That distinction between deciding and falling is not merely descriptive. It reflects the actual mechanical behavior of a material that has both liquid and near-solid properties simultaneously, each one present in a different proportion depending on the time scale over which the force is applied. The temperature at which glucose in honey crystallizes most readily sits at approximately 14 degrees Celsius, within a broader range across which the process accelerates and slows, rather than switching cleanly on or off. Below this point, glucose molecules slow dramatically and begin to seek out the geometric arrangement that their shape prefers. Above it, the same molecules remain in suspension, circulating through the liquid phase without committing to a fixed position. The exact rate at which a jar of honey will crystallize is not perfectly predictable, even with knowledge of the sugar ratio. The precise nucleation behavior, which particle will initiate the first crystal, at which moment, in response to which microscopic condition, remains one of those details that science has measured broadly, but not yet fully mapped at the level of individual events. That is not a gap in the science, so much as a reminder that even in a jar of honey sitting quietly on a shelf, there are things happening that are not yet entirely legible. What the hand holds when it holds a jar of this material is a liquid that has almost completed a process it began somewhere above a field of flowers, carried inside a bee at 35 degrees, worked and concentrated across days of quiet labor, and sealed into a state that is now neither fully liquid nor fully solid, but something particular to itself, a material whose chemistry settled into its current arrangement and, for the moment, maintains it. At 35 degrees, honey becomes considerably more fluid than it is at 15 degrees. It is as though the higher temperature finally overcomes its stubbornness, and honey, left with no choice, begins to soften and lose its thickness. That jar on the shelf, the one that has already begun to cloud from the inside, contains a process that is not disorder. I mentioned earlier that when honey is kept undisturbed for a long time, it undergoes a process of gradual crystallization. And I will admit, the first time I saw it, my immediate thought was that it had gone bad. It had not. This is simply a natural process. If you go looking for your jar with enthusiasm and find the honey has crystallized, do not be disappointed. It is still perfectly good. Take a taste, and you will find that, like a friend who never lends money, it has not given away a single drop of its flavor in all that time. If honey could speak, it would say, "Do not let my appearance fool you. My taste has not changed one bit. So what if my clear amber color looks a little cloudy now?" The crystalline structure that glucose builds inside honey is a monoclinic lattice, which is a way of describing a three-dimensional repeating pattern in which the building units are not all equal, giving the crystal a slightly tilted, asymmetric quality compared to the perfect cubic lattices of table salt or iron. The practical effect of this geometry is visible in the texture of set honey. The crystals are fine, close-packed, and relatively uniform in size when crystallization happens slowly and at a stable temperature, producing a smooth, spreadable texture. When it happens quickly, because the temperature dropped suddenly, or because the nucleation was initiated by a large particle, the crystals are larger, coarser, and the texture becomes noticeably grainier. The speed of the process writes itself directly into the physical result. Beneath that surface quality lies the question of what initiated the process in the first place. Every crystal in a jar of honey began at a nucleation site, a physical point around which the first glucose molecules gathered and locked into their preferred pattern, providing a template that neighboring molecules then followed. These sites are not impurities in any negative sense. They are pollen grains, beeswax traces, microscopic air bubbles, and occasionally fragments of existing glucose crystal carried forward from a previous batch. Raw, unfiltered honey, with its full complement of pollen and wax traces, crystallizes faster than heavily filtered honey, which has had many of its natural nucleation sites removed. The filtering does not change the chemistry, it simply removes the scaffolding that the crystallization process prefers to build upon. A single pollen grain inside a jar of honey is small enough to be invisible without magnification. Honey can contain tens of thousands of pollen grains per 10 grams, depending on how much filtration it has undergone. lightly processed honey retaining considerably more than its heavily filtered equivalent. That count is, in practice, the botanical fingerprint of the landscape the bees worked. Pollen analysis, a formal field called melissopollenology, can identify the geographic origin of a honey sample with considerable precision by examining the species distribution of those grains under a microscope. A jar labeled as from a specific region carries within the honey itself actual physical evidence of the flowers that produced the nectar that produced it. The structure holds the history. It always has. The hardness of crystallized honey is not a property that receives much formal attention, because honey is not typically classified on the Mohs scale, a scale designed for minerals. But the question is not entirely without an answer. Individual glucose monohydrate crystals, the specific crystalline form glucose takes inside honey, have a measurable rigidity at low temperatures that allows them to resist deformation under light pressure. A completely crystallized block of honey at refrigerator temperature behaves under a blade more like a dense wax than like a frozen liquid. It can be sliced. It holds its shape when cut. It does not spring back or slump. The crystalline network has, for the duration of that temperature, taken on the structural behavior of a soft solid. Going one level further into the structure, the glucose crystals in set honey are not dry. They are glucose monohydrate. Each glucose molecule in the crystal lattice is paired with exactly one water molecule, bound into the structure rather than free in solution. This water is not available to the surrounding liquid phase. It is held, structurally, inside the crystal itself, locked into the repeating pattern. This matters for the overall stability of the honey, because water that is structurally incorporated into a crystal cannot participate in microbial activity. The crystallization process is not simply a physical change in texture. It is also, in a quiet way, a further step in the stabilization of the material, removing water from the phase where it might cause problems and incorporating it into a phase where it cannot. The fructose in the same jar is doing something different. At 38.5% of honey's composition, fructose is present in greater quantity than glucose, but it is far more reluctant to crystallize. The molecular geometry of fructose, which is a structural isomer of glucose, meaning it contains exactly the same atoms in a different spatial arrangement, does not lend itself as naturally to lattice formation. Fructose tends to remain in the liquid phase, even as the glucose around it organizes into crystals, becoming gradually more concentrated as the glucose is removed from solution. This increasing fructose concentration changes the character of the surrounding liquid. It becomes more hygroscopic, more inclined to draw moisture from the surrounding air, and more resistant to further crystallization. The honey sets partly because the glucose decides to, and stays liquid partly because the fructose declines to follow. What becomes interesting at the molecular level is the interaction between the two phases, the crystalline glucose network and the supersaturated fructose-rich liquid surrounding it as the crystallization proceeds. The ratio between them is not fixed. It changes over time, slowly, as more glucose molecules encounter nucleation sites and join the growing crystal. A jar of partially crystallized honey is, in this sense, a system in mid-process, neither committed to one state nor the other, the balance between solid and liquid shifting incrementally with each day that passes. The visual evidence of this, the clouding, the opacity, the slight separation between a clearer liquid layer at the top and a denser crystalline mass at the base, is simply the macro-scale expression of millions of simultaneous molecular decisions happening at a rate too slow to watch directly. There is a further detail here that connects the grain of crystallized honey to its color. Finely crystallized honey, set slowly at a stable, cool temperature from a nucleation-rich starting point, scatters light more evenly than coarsely crystallized honey. The smaller the crystals, the whiter or more opaque the final texture appears, because the greater number of crystal surfaces intercepts and scatters light in more directions simultaneously. This is why commercially creamed honey, honey that has been deliberately seeded with fine crystals and held at a controlled temperature during setting, has that characteristic pale, smooth, almost white appearance. The color has not changed because the chemistry has changed, but because the crystal size has changed, and the crystal size determines how the material interacts with light. The jar is not a different honey. It is the same honey, having made a different structural choice. Perhaps many of us, before tasting something, bring it to our nose first. And yes, when you open a jar of honey for the first time, a light scent comes from it, as if whispering, what you are smelling right now is going to be something very sweet. It is not a sharp smell, but the nose catches it. I personally compare the smell of honey to the smell of medical iodine from a pharmacy, like a lighter, slightly sweeter version of it, though this varies from honey to honey. The cap comes off, the scent arrives, and the interesting part is that within minutes it is gone. It does not come back. The second time you open the same jar, that first smell is no longer there to greet you. That has been my own experience. Adjacent to that property, and related to it, is the way the smell of honey changes with temperature. Warmed honey releases its volatile compounds more readily, which is why heated honey has a stronger, more complex aroma than honey at room temperature. The warmth gives the lighter molecules enough energy to escape the liquid surface and reach the air in greater concentration. Cold honey, by contrast, holds its aromatics closer. A jar taken directly from a cool room and opened will smell faint, almost neutral, and then as it warms on the shelf will gradually develop more of its character. The smell, like the texture and the color, is not a fixed property. It is a condition of the material at a specific temperature, at a specific moment, having been sealed for a specific length of time. Looking at a jar of honey and thinking it is simply food, that is understandable. But what is happening inside it may surprise you. The crystals are growing. The aromatics, as I mentioned earlier, are waiting for the first opportunity to escape. The color is shifting, the way people change as they grow. Glucose is moving in one direction, fructose in another. All of it is happening without anyone's knowledge, in its own course. You may forget the jar on the shelf, but the honey does not stop. It continues its natural processes quietly, slowly, without rushing. At the smallest scale of that crystalline structure, smaller than the crystal, smaller than the glucose monohydrate unit, smaller than anything the hand can register, the atoms themselves are holding a position. We learn that the honey we spread on our bread without a second thought is, in reality, passing through extraordinarily complex processes. Honey moves through these processes and continues to. But even as all of this unfolds, honey does not forget to rest, in its own way, at its own pace. This information may be familiar to some, new to others. It does not matter either way. Whether you know it or not, the atoms inside that jar are doing their work at their own tempo. The position those atoms hold is not static in the way that a stone is static. At any temperature above absolute zero, which is every temperature at which honey has ever been examined, the atoms inside the crystal lattice are vibrating, not moving in any particular direction, not drifting out of position, vibrating in place around their fixed point in the lattice, with an amplitude that is directly proportional to the temperature of the material. Warm the honey and the vibrations increase. Cool it and they diminish. The atoms stay where they are in the lattice, but they tremble with more or less energy depending on what the surrounding temperature is doing. This is not a poetic observation about restlessness. It is a physical reality that has direct, measurable consequences for how honey behaves under every thermal condition it encounters. Honey's response to heat begins well before the temperatures that cause any visible change. At 25 degrees Celsius, a warm room, a kitchen in summer, the viscosity of honey has already dropped significantly compared to 15 degrees, the molecules moving more freely through the liquid phase as the thermal energy increases. At 40 degrees, it pours like a heavy oil. At 50 degrees, it flows almost freely. None of these temperatures have altered the chemistry. They have simply loosened the molecular interactions that give the honey its resistance to movement, temporarily, reversibly, in direct proportion to the heat applied. Above 50 degrees Celsius, something different begins. The enzyme diastase, one of several enzymes present in honey introduced by the bees during processing, begins to lose its functional structure. Enzymes are proteins, and proteins are constructed in three-dimensional shapes that are essential to their function. Heat disrupts those shapes, unfolding the protein the way steam softens a folded piece of paper, gradually, then completely, until the original geometry is gone and cannot be recovered by cooling. The temperature at which diastase begins to denature is not sharply defined. The process is gradual, accelerating between 50 and 60 degrees, and largely complete above 70. Honey that has been heated above these temperatures retains its sugars, its color, its weight, and its approximate flavor, but it has lost something that was present before the heat, an enzymatic capacity that cannot be restored simply by allowing the honey to cool. The thermal conductivity of honey, how quickly it accepts or transmits heat from whatever it contacts, is low by the standards of most liquids, approximately 0.5 watts per meter Kelvin, which sits below water at 0.6 watts per meter Kelvin, and far below metals, which range from tens to hundreds of watts per meter Kelvin. The practical consequence of this low conductivity is that honey warms and cools slowly and unevenly. A jar removed from a cold room and placed in a warm kitchen will be noticeably warmer at the surface than at the center for a considerable time, minutes, sometimes hours for a large jar, as the heat from the surrounding air conducts inward through the honey at its own unhurried pace. The surface softens, the core stays firm. The gradient between them is real and measurable, and it persists far longer than most people would predict. This same low conductivity is what makes honey useful as an insulating layer in some preservation contexts. But that is not the most interesting thermal story honey contains. The more interesting one is what happens during the bee's own processing inside the hive, where temperature management is not incidental but central to the work being done. A working honeybee hive maintains its interior at approximately 35 degrees Celsius year-round through the collective metabolic activity of the colony. This temperature is not accidental. It is actively regulated. Bees clustering together to generate heat in winter, bees fanning at the hive entrance to move air through the combs in summer. The honey being processed inside the hive is therefore held at a stable, warm temperature throughout its concentration, a condition that keeps the honey liquid enough to be worked, keeps the enzymatic activity at an efficient rate, and provides the thermal environment in which evaporation of water can proceed at the required pace. That evaporation is the central thermal event in honey's production. Freshly collected nectar contains between 60 and 80% water by weight. The finished honey that will be sealed with wax contains below 18.6%, a threshold that is not arbitrary, but the precise point below which the water activity of the honey drops low enough to prevent fermentation. Water activity is a measure not of total water content, but of how available the water is to participate in chemical and biological processes. Getting from 60 to 70% water down to below 19% requires removing an enormous proportion of the original liquid content. The bees accomplish this through fanning. Worker bees beat their wings approximately 200 times per second, but not to fly. They stand in place, beating their wings rapidly to push the warm, moisture-heavy air from inside the hive outward so the honey can thicken. It is as though the bees have made an agreement with the honey. We will drive out your moisture. Hundreds of them do this simultaneously, in shifts, for days at a time. The unending hum you hear from outside a working hive is exactly this. The heat produced by the colony as a byproduct of this metabolic work is itself a resource. Bees are warm-blooded, not in the mammalian sense, but in the functional sense that they generate significant heat through muscular activity, and the colony manages that heat collectively. In cold weather, bees shiver their flight muscles without opening their wings. The shivering generates heat. The same way I try to keep moving when I am cold, muscles working, warmth following. Bees do the same. No wing movement, just heat. The temperature sensitivity of honey's crystallization connects directly to these thermal realities. At 14 degrees Celsius, glucose crystallization accelerates. Between 25 and 30 degrees, it slows. Above 40 degrees, the crystals already present in a jar of honey will dissolve back into solution, the thermal energy disrupting the lattice geometry the crystals had assembled, returning the glucose to its liquid state. This reversibility is real. Honey that has crystallized can be returned to liquid form by gentle, sustained warmth without permanently altering its chemistry, provided the temperature is kept below the enzymatic denaturation threshold. The lattice dissolves, the molecules re-enter solution, the honey clears. The process does not remember having happened. Moving deeper into the thermal exchange, the energy involved in this dissolution is not passive. Breaking the bonds of a glucose monohydrate crystal requires energy, thermal energy, supplied from the heat source. The material absorbs heat as it liquefies, in exactly the same way that melting ice absorbs heat without immediately rising in temperature. A jar of crystallized honey placed in warm water will warm more slowly than an equivalent jar of liquid honey, because some of the thermal energy entering the crystallized jar is going directly into the work of breaking apart the crystal lattice rather than raising the temperature of the material. The crystal is, in this limited sense, a form of thermal storage. It holds latent energy in its structure and releases it when the structure dissolves. The smell released by gently warmed honey carries the evidence of this thermal activity. The lighter volatile compounds, which are held in solution at room temperature by the viscosity of the surrounding liquid, are released more freely as the viscosity drops and the molecular motion increases. A jar of honey warmed slowly in a water bath will develop a richer, more complex aromatic profile than the same jar at room temperature. The lighter floral notes emerging first, then the heavier aromatic compounds as the temperature continues to rise. The warmth is not adding anything to the honey. It is simply reducing the resistance that had been holding those compounds close to the liquid surface. There is a thermal threshold that marks a clear transition in honey's behavior, a point above which the material is no longer, in any practical sense, the same material it was before. This threshold sits at around 70 to 80 degrees Celsius, sustained over time, where the combination of enzymatic denaturation and accelerating Maillard browning, the same slow color-deepening reaction noted earlier, but now proceeding at a greatly accelerated rate, produces irreversible changes in color, flavor, and enzymatic content. Honey heated to this range and held there will darken, its flavor will shift toward caramel, and its enzyme content will fall to negligible levels. The sugar structure remains intact, the water content remains low, but the biological and enzymatic signatures of the original material, the specific profile that distinguishes one honey from another, the record of the flowers and the landscape, will have been erased. The heat that the bees so carefully managed, maintaining that 35-degree interior with metabolic precision, exists at exactly the right point to keep the processing running without triggering any of these degradation thresholds. Bees have no thermostat, no instrument to measure the inside of the hive, and yet they maintain it at exactly the right point, not too hot, not too cold. They do this with nothing but the coordinated beating of their wings. If they could not hold that temperature, the enzymes inside the honey would be destroyed, and the honey would become nothing more than thick sugar water. The bees may have no awareness of any of this, and yet they do it perfectly. The chemistry that those enzymes produce, in particular the specific reaction that generates hydrogen peroxide within the honey, belongs to a deeper layer than the thermal one. Honestly, the fact that bees maintain the temperature inside the hive so precisely without any instrument to measure it genuinely surprised me. We use devices just to regulate the temperature of an ordinary room. They do it without knowing they are doing it at all. I had no idea that the hydrogen peroxide we buy at the pharmacy actually exists inside honey as well. Most of us know what hydrogen peroxide is. We put it on a cut, it foams. Its presence inside honey is not accidental. The honey's own chemistry produces it. Could it be harmful? No. The concentration is far too low, entirely safe. This is something that would never have crossed my mind. The enzyme responsible is glucose oxidase. Bees introduce it into nectar during processing. It is secreted from the hypopharyngeal glands, which sit in the bee's head and open into the mouth parts, and it is transferred to the nectar during the repeated ingestion and regurgitation that forms part of honey's early stage concentration. Glucose oxidase catalyzes a reaction between glucose and dissolved oxygen, producing two products, gluconic acid and hydrogen peroxide. The hydrogen peroxide is present at low, steady-state concentrations that the honey's own chemistry manages, not accumulating to harmful levels, but maintaining a persistent, low-intensity antimicrobial environment within the liquid. The gluconic acid has a separate role, contributing to honey's overall acidity. The pH of honey sits between 3.2 and 4.5, firmly in the acidic range, roughly comparable to a tomato. This acidity is a collective contribution from several organic acids present in honey, of which gluconic acid is the most abundant, typically comprising more than 70% of honey's total organic acid content. The acids arrive from two directions. Some are present in the original nectar, and some are produced enzymatically during processing, gluconic acid being the principal enzymatic contribution. The combined effect is a pH environment that is hostile to many microorganisms, which have their own preferred pH ranges for growth and cannot sustain normal metabolic activity at values much below 4.5. Honey's acidity is not the only mechanism protecting it, but it is one of the more consistent ones, present throughout the material and maintained at a stable level over time. The molecular structure of gluconic acid is worth pausing on. It is a simple 6-carbon molecule, the same carbon backbone as glucose, modified by one oxidation step that replaces the aldehyde group at one end with a carboxylic acid group. The reaction that produces it is, in molecular terms, a small but consequential modification. One chemical group exchanged for another, the carbon skeleton left intact, the charge and reactivity of the molecule changed entirely. This is the kind of transformation that organic chemistry performs constantly in countless materials and biological systems, a small structural change producing a large functional difference. Gluconic acid is gentler and more soluble than many of the stronger organic acids, which is part of why honey's acidity is stable and mild rather than volatile or aggressive. In another layer of this material's behavior, the relationship between these three chemical properties, the acidity, the hydrogen peroxide, and the osmotic pressure from the high sugar concentration, and the way they interact with any microorganism that enters the honey. None of these three mechanisms operates in isolation. They are simultaneous, overlapping, and in some respects mutually reinforcing. The acidity disrupts the pH balance that bacteria require to function. The hydrogen peroxide attacks cellular structures directly. The osmotic pressure, which operates through a different mechanism entirely, removes water from bacterial cells through the physics of concentration gradients, essentially desiccating any organism that cannot tolerate the extreme sugar density of its surrounding environment. Osmotic pressure in honey is not gentle. The osmolarity of honey sits well above the internal osmolarity of most bacterial cells, by a margin large enough that the concentration gradient between the inside of a bacterial cell and the surrounding honey creates a powerful and irresistible physical force drawing water outward through the cell membrane. The cell attempts to maintain its internal water balance. The surrounding honey prevents it. The result, for most bacteria, is rapid dehydration and cell death, not through any active mechanism on honey's part, but simply through the passive physics of two fluids at vastly different concentrations reaching toward equilibrium through a semi-permeable barrier. The acidity inside honey is roughly comparable to that of a tomato, with a pH between 3.2 and 4.5. That puts it in the same range as something I personally use and enjoy in salads and cooking. We notice the acidity in a tomato, but not in honey. I tested this myself once. While peeling a tomato in the kitchen, the juice landed on my hand and started to sting. That is the acidity making itself known. In honey, it is always there, stable and consistent, and it is one of the mechanisms the material uses to protect itself. This osmotic mechanism is the primary reason honey with water content below 18.6% is self-preserving. Above that threshold, if fermentation-capable yeasts are present and the water content is high enough for those yeasts to maintain their own water balance against the osmotic gradient, fermentation becomes possible. The yeast cells that survive in sufficiently diluted honey are osmophilic species, meaning they have adapted to high sugar environments and can tolerate osmotic pressures that eliminate most other organisms. Below the 18.6% threshold, even these adapted species cannot sustain activity. Honey's water activity at or below this threshold drops to a level at which almost no microorganism can sustain growth. The water is present, but it is not available, bound into the molecular interactions between the sugars, incorporated into the crystal lattice, or held in configurations that prevent it from participating in the processes that yeasts require. The honest assessment of honey's preservation chemistry requires acknowledging that the relative contributions of these mechanisms, osmotic pressure, hydrogen peroxide generation, gluconic acid acidity, and several additional minor antimicrobial compounds to its overall long-term stability are not precisely quantified. Research on honey's antimicrobial properties has produced a consistent picture of the effect, but the exact proportional contribution of each mechanism to that effect remains a matter of ongoing investigation. What is measurable, clearly and reproducibly, is the outcome. Properly processed and stored honey does not support microbial growth, and the available evidence suggests that this stability is not the product of a single mechanism, but of several operating simultaneously. The full accounting of their individual weights is still being assembled. In addition to these primary chemical mechanisms, honey contains a category of compounds called polyphenols, plant-derived molecules present in the original nectar, carried through into the finished honey without significant alteration. Polyphenols are a broad structural family. They share a basic aromatic ring structure decorated with hydroxyl groups at various positions, and this structural feature gives them chemical complexity that contributes to honey's overall chemical complexity. Some polyphenols act as antioxidants, molecules that interact with and neutralize reactive oxygen species, which are chemically aggressive molecular fragments that can damage biological structures over time. Others contribute to flavor and color. The polyphenol content of a given honey varies significantly with the plant source, which is why darker honeys, particularly buckwheat honey, tend to have considerably higher polyphenol concentrations than lighter varieties. The color and the chemistry are again aligned. One polyphenol compound deserves specific attention: methyl glyoxal, abbreviated MgO. Present in most honeys at trace concentrations, it occurs at dramatically elevated levels in honey produced from the flowers of the manuka tree, native to New Zealand and southeastern Australia. Methyl glyoxal is a reactive carbonyl compound, a small molecule with a chemical group that interacts readily with proteins, disrupting their structure in ways that have measurable biological consequences. The concentration of MgO in manuka honey can reach several hundred milligrams per kilogram, compared to trace amounts in most other varieties. The chemistry of this elevation is not fully resolved. The leading explanation involves a precursor compound in manuka nectar that converts to MgO within the honey over time, but the precise pathway remains an active area of investigation. What is clear is that the compound is real, measurable, and specific to this botanical source. The mechanism of its accumulation is still being examined. The bonding within honey's sugar molecules, the covalent bonds that hold each glucose and fructose unit together, are among the most stable chemical bonds in organic chemistry. A covalent bond is formed when two atoms share electrons rather than transferring them, creating a connection that requires significant energy to break. The carbon-carbon and carbon-oxygen bonds that make up the backbone of glucose and fructose are robust under ambient conditions, resistant to simple hydrolysis at the pH levels found in honey, and stable across the temperature range honey normally encounters in storage. This is the molecular foundation of honey's long-term chemical stability. The primary structural units simply do not break down easily. The sugars that were present when the honey was first sealed are, at the molecular level, the same sugars present 3,000 years later in a sealed vessel, not because nothing has happened, but because the bonds that hold those molecules together are too stable to be disrupted by time and ambient conditions alone. The electron behavior within those covalent bonds, the way the shared electrons are distributed between the bonded atoms, determines the chemical character of each bond. In the carbon-oxygen bonds of the hydroxyl groups on glucose and fructose, the electrons are not shared equally. Oxygen, being more electronegative, draws the electron density slightly toward itself. This unequal sharing creates a slight polarity in the bond, a faint electrical asymmetry that makes the hydroxyl groups inclined to interact with other polar molecules, particularly water. These interactions are what make glucose and fructose so highly soluble. The polar hydroxyl groups form hydrogen bonds with water molecules, surrounding each sugar molecule with a shell of ordered water that holds it in solution. When the water concentration drops below a critical threshold, as it does in finished honey, there is no longer enough water to maintain these shells for every sugar molecule simultaneously. The sugars interact with each other instead, their hydroxyl groups forming hydrogen bonds between adjacent molecules rather than with water. This mutual interaction is what gives concentrated honey its viscosity, its structural cohesion, and its reluctance to flow. Set alongside that molecular cohesion is something that operates at a longer time scale than the daily chemistry of the material, a process that unfolds over years and decades, leaving a record in the color and the flavor of the honey that a careful examination can read. The processes inside honey are numerous, and none of them work alone. Just as bees work together to maintain the temperature of the hive, the processes inside the honey work together as well. I have heard many times that honey kills bacteria, but it is worth remembering that honey does not fight bacteria. The physics does. The color of honey is not fixed at the moment the wax cap is sealed. The chemistry inside continues, slowly, without interruption, across months and years, and the material that emerges from a sealed jar after a decade is measurably different from the material that went into it, in ways that are legible to anyone who looks carefully at the color, the smell, and the behavior on a spoon. This is not deterioration. It is the continuation of a process that was already underway before the sealing occurred, proceeding now in the absence of outside influence, driven entirely by the internal chemistry of the material and the conditions of its storage. The Maillard reaction, introduced earlier as a browning process, operates in honey as an extremely slow, low-temperature version of the same chemistry that occurs rapidly in a hot pan. The reaction requires two categories of compound to be present simultaneously. A reducing sugar, glucose and fructose both qualify, and an amino acid or protein. Honey contains both. The amino acids are present in small but measurable quantities, contributed by the bee's enzymatic additions and by trace amounts carried over from the original nectar. At ambient temperature, the reaction proceeds at a rate so slow that visible browning takes months to years, depending on storage conditions. At elevated storage temperatures, a jar left in a warm room rather than a cool, dark space, the rate accelerates measurably because the Maillard reaction's rate approximately doubles for every 10 degrees rise in temperature, following the general kinetic principle that chemical reactions proceed faster as the thermal energy of the reactant molecules increases. The products of the Maillard reaction in honey are not simple. The reaction generates a cascade of intermediate compounds, including molecules called amidori products, formed in the first step, and then a diverse range of aromatic compounds, colored polymers, and flavor molecules produced in subsequent steps. One of the measurable products is hydroxymethylfurfural, abbreviated HMF, a compound formed from the degradation of fructose under acidic conditions at elevated temperatures and produced more slowly at ambient temperatures over time. HMF concentration is used as a quality indicator in commercial honey grading. Fresh honey has very low HMF levels, typically below 5 milligrams per kilogram, and HMF increases predictably with both storage time and storage temperature. A honey with HMF levels above 40 milligrams per kilogram is generally considered to have been either overheated or stored for too long under warm conditions. The number is a record. The honey carries its own history in measurable chemical form. Honey changes over time. Many people describe it as deepening. The floral notes fade, the heavier caramel character grows. Open the same jar after a few years and it has shifted. Is that a bad thing? No. Most things change over time, physically, internally, sometimes both at once. Compare honey to other foods, and some go bad within a week. Honey never abandons its stubbornness. The lighter end of the flavor spectrum shortens. The heavier end extends. The overall profile moves towards something more concentrated, darker at the edges, with less of the immediate brightness that characterizes fresh honey. The crystallization state of honey also evolves over time, independent of temperature changes. Honey that has been stored for several years without deliberate remelting will typically show complete or near-complete crystallization, as the glucose molecules continue to find nucleation sites and join the growing crystal network. The crystal size distribution tends to coarsen with age, larger, fewer crystals replacing the fine initial network, as a process called Ostwald ripening. Smaller crystals, which have a higher surface energy to volume ratio, gradually dissolve back into solution, while larger crystals grow at their expense. The driving force is purely energetic. Larger crystals are thermodynamically more stable than many small ones, and the system moves, slowly, toward the lower energy configuration. The visual result is a coarser, sometimes grainier texture in old crystallized honey, compared to honey that was deliberately seeded and crystallized under controlled conditions. Fermentation is the chemical change most capable of disrupting honey's long-term stability, and it operates through a narrow set of conditions. Osmophilic yeasts, primarily species of Zygosaccharomyces, can survive in the high-sugar environment of honey and will begin active fermentation if the water content rises above the stability threshold. The water content of sealed honey does not spontaneously rise under normal conditions. It is fixed at the time of sealing. But honey that is not yet fully processed, with a water content still above 18.6%, or honey that is stored in a humid environment with inadequate sealing, can absorb moisture through a permeable container or an improperly sealed lid. the hygroscopic character of the honey, its tendency to draw moisture from surrounding air, that is a source of its antimicrobial power under correct conditions, becomes a vulnerability under incorrect ones. If water activity rises above 0.6, fermentation becomes possible. The yeasts, which have been present the entire time in dormant form, resume activity. The honey begins to produce carbon dioxide, alcohol, and organic acids. The smell changes. The character of the material is altered in a direction that is not reversible. I have been talking about honey's stubbornness, but how does it keep going like this? Honey is not eternal. It needs certain conditions. Water content must stay low, temperature must stay cool, the lid must be sealed properly. These are not difficult conditions, but if they are not met, honey cannot protect itself. The same is true for things I use at home. Ignore the storage rules, and something that would last 2 years is gone in 2 months. Honey is no different. The enzymatic activity of honey diminishes over time, even under ideal storage conditions. Diastase, one of the primary enzyme markers used to assess honey quality, loses activity gradually at ambient temperature at a rate that varies with storage temperature. At 20 degrees Celsius, diastase activity in well-processed honey can remain measurable for several years. At higher storage temperatures, the decline is faster. The diastase number, a formal measurement of diastase activity, is used in honey quality standards in several countries as an indirect indicator of freshness and thermal history, on the basis that diastase degrades predictably over time and under heat. A low diastase number in a honey sample indicates either age or heat exposure, or both. The enzyme is a clock that runs in one direction. Adjacent to that aging chemistry, and worth distinguishing from it, is the behavior of honey's aromatic compounds under different storage conditions. The volatile fraction of honey, those 600+ compounds responsible for the characteristic smell, is not uniformly stable over time. The lighter compounds, with lower molecular weights and higher vapor pressures, escape slowly through even sealed containers. The heavier aromatic compounds, with higher molecular weights and lower vapor pressures, are retained more completely. The result is that the aromatic profile of aged honey is skewed toward the heavier end of the spectrum. Not in any simple sense poorer, but shifted, the high notes having diminished and the low notes remaining. A beekeeper who opens a jar from several years ago notices first what is missing, the bright, immediate floral quality, and then what remains, which has a depth and heaviness that fresh honey typically lacks. The color record left by all of this slow chemistry, the Maillard browning, the polyphenol oxidation, the HMF accumulation, is readable by anyone who keeps honey long enough to observe it. A jar sealed at a pale amber and stored in a warm kitchen for several years will be significantly darker at the end of that period than at the beginning. The same jar stored at a steady cool temperature will be marginally darker. Some browning is thermodynamically inevitable, but considerably less so. The color difference between the two jars is a direct, visual record of the difference in their storage temperature across the decade. The material keeps its own record of conditions, every time, without variation, without error. The account it keeps of itself is always honest. The long-term stability of honey under ideal conditions, sealed, below 20 degrees, dark, dry, is not merely theoretical. archaeological evidence has confirmed it. Sealed honey samples recovered from Egyptian tomb contexts dated to approximately 3,000 years before the present have been found intact and in an edible state, not merely preserved as a desiccated relic, but with their sugar chemistry essentially intact, their pH within the expected range, and their physical properties consistent with honey that has simply been stored for a very long time rather than fundamentally altered. The evidence for this is genuine, though it warrants the qualification that not all samples reported in popular literature have been subjected to rigorous chemical analysis. The best documented cases are specific and careful. The general principle they support, that properly stored honey resists chemical breakdown over millennial timescales, is consistent with everything the chemistry predicts. What that millennial stability requires at the molecular level is simply that the conditions be maintained. The material does not age in the way that organic materials typically age. It does not rot. It does not oxidize into incoherence. It changes. HMF rises, enzymes diminish, color deepens, aroma shifts. But the changes proceed so slowly under ideal conditions that they are imperceptible over a human lifetime of storage. The material that was placed in a jar in one century can be opened in another and still be recognized chemically and physically as the same substance, not unchanged, but continuous. The reason that continuity possible lives at a level below the chemistry of the sugars, below the activity of the enzymes, below the behavior of the Maillard intermediates, at the level of the lattice itself and the atoms within it. Honey makes its way to our table, having passed through long processes, never abandoning its stubbornness. Of course, certain conditions are needed for that to happen, and we talked about those. Like everything, honey has its limits too. If I say that this research stirred something like genuine affection in me toward honey, I would not be wrong. It feels as though a connection formed between us. Now, the next time I spread it on bread, everything we discussed here will run through my mind again, like a tape on repeat, in the best possible way. The lattice is not a metaphor. It is a physical structure, a three-dimensional arrangement of atoms held in fixed spatial relationships by the bonds between them, repeating in all directions with a regularity that is absolute at low temperatures and increasingly disturbed by thermal vibration as the temperature rises. In the glucose monohydrate crystals inside honey, this lattice is monoclinic, a geometry in which three axes of different lengths meet at angles that are not all 90 degrees, giving the crystal a slightly oblique character that distinguishes it from the simple cubic symmetry of sodium chloride or the hexagonal symmetry of ice. Each unit cell of the glucose monohydrate lattice, the smallest repeating unit that contains all the geometric information needed to construct the entire crystal, contains 2 glucose molecules and 2 water molecules, arranged in a specific spatial relationship that is preserved identically across every unit cell in the crystal. The cell dimensions are approximately 0.77 nanometers along one axis, 0.86 nanometers along another, and 0.48 nanometers along the third, with angles between them of 90 degrees, 94 degrees, and 90 degrees respectively. These numbers are not approximations for the purpose of illustration. They are the measured lattice parameters of glucose monohydrate, determined by X-ray crystallography. Every crystal of glucose monohydrate grown anywhere in the world from any solution will have these dimensions, not approximately, but exactly within measurement precision. The lattice is not learned from its environment. It is intrinsic to the molecule. The water molecules incorporated into the lattice are held in place by hydrogen bonds, the same type of interaction that governs the behavior of water in all its contexts, but here organized into a specific, non-random geometry. Each water molecule in the unit cell donates its hydrogen atoms to oxygen atoms on adjacent glucose molecules and accepts hydrogen bonds from other parts of the network, forming a web of connections that integrates the water fully into the crystal structure, rather than allowing it to exist as a distinct phase within the lattice. This integration is what makes glucose monohydrate a stoichiometrically defined compound, not glucose with some water present, but a specific chemical entity in which the glucose and water are present in a 1-to-1 ratio by design. The lattice demands exactly one water molecule per glucose molecule, and it organizes them accordingly. Hydrogen bonds, the connections that hold together the lattice, that hold water molecules to each other, that give honey its viscosity, that make DNA maintain its helical form, are not covalent bonds. They do not involve the sharing of electrons between atoms. They are weaker, electrostatic attractions between a hydrogen atom bonded to a strongly electronegative atom, oxygen or nitrogen, and another electronegative atom nearby. In isolation, a single hydrogen bond is approximately 20 times weaker than a typical covalent bond. But hydrogen bonds do not occur in isolation in materials like honey. They occur simultaneously in very large numbers. Each glucose molecule in solution participates in multiple hydrogen bonds with surrounding water molecules and other sugar molecules, and the cumulative effect of this dense network of individually weak connections is the macroscopic viscosity and structural coherence that the hand feels when it stirs or lifts or pours. Strength through multiplicity, each connection modest, the total formidable. The electrons that participate in these hydrogen bonds and in the covalent bonds of the glucose backbone are not stationary. In the quantum mechanical description of molecular structure, electrons do not orbit in fixed paths. They occupy probability distributions, regions of space in which the electron is more or less likely to be found at any given instant without a defined trajectory. The shape of these distributions is determined by the molecule's geometry, the energies of the atomic orbitals involved, and the interactions with neighboring atoms. In the carbon-oxygen bonds of glucose, the electron distribution is asymmetric, weighted toward the oxygen, as noted earlier, and this asymmetry is what produces the polarity that makes hydroxyl groups so inclined to form hydrogen bonds. The shape of the electron distribution is, in this sense, the molecular cause of everything that follows: the viscosity, the crystallization, the solubility, the osmotic pressure, and the stability. At the scale of individual atoms, the thermal vibration mentioned at the start of this chapter has a specific character in the glucose monohydrate lattice. Different atoms vibrate with different amplitudes at the same temperature. Lighter atoms vibrate more energetically than heavier ones for a given amount of thermal energy, in the same way that a lighter ball on a spring oscillates more widely than a heavier one, given the same push. Hydrogen atoms, being the lightest, vibrate with the largest amplitude. Their position within the crystal is the least precisely defined. The heavier carbon and oxygen atoms vibrate within smaller envelopes. The overall effect is that the lattice at room temperature is not perfectly ordered in a static sense. It is a dynamically ordered system, a pattern in which each atom's average position is exactly determined by the lattice geometry, but each atom's instantaneous position oscillates around that average with an amplitude that is proportional to temperature. The crystal is, at any given instant, slightly imperfect. Over time, averaged across billions of vibrations per second, it is exact. This vibration is not incidental. It is the physical mechanism by which the crystal maintains its own internal equilibrium. Each atom in the lattice pushes and pulls against its neighbors through the bonds connecting them, and the vibration propagates through the structure as thermal energy is distributed throughout the material. When a crystal of glucose monohydrate is cooled, the vibrations diminish. The atoms settle closer to their equilibrium positions. The lattice contracts slightly, the thermal expansion of the crystal run in reverse. When the crystal is warmed, the vibrations increase. The lattice expands fractionally, and at the threshold temperature, where the vibrational energy becomes sufficient to overcome the bond energies holding the lattice together, the crystal dissolves. The temperature at which glucose monohydrate loses its crystalline structure, releasing its water of crystallization and passing into liquid solution, sits at approximately 83 degrees Celsius, the point at which thermal vibration has grown sufficient to disrupt the hydrogen bond network holding the lattice in place. Below that temperature, in the dark interior of a sealed jar kept at room temperature, the vibration continues at its ambient level, thousands of millions of oscillations per second around fixed points in every atom of every crystal. The pattern does not degrade. The positions do not drift. The crystal does not slowly rearrange itself into something else. It holds its geometry through the vibration rather than despite it. The oscillation is what equilibrium looks like at the atomic scale. Honey may look still from the outside, but that is not the full picture. There are many processes happening inside it that we cannot see. Do not let its thick, calm appearance fool you. The electron configuration of glucose, the arrangement of electrons in each carbon, oxygen, and hydrogen atom, is what the molecule's chemistry reduces to at the deepest level of description available by current methods. Each carbon atom in the glucose backbone shares its 4 available bonding electrons with neighboring atoms in specific geometric arrangements. The tetrahedral geometry of sp3 hybridized carbon in which 4 bonds extend outward at angles of approximately 109.5 degrees from the central atom, producing the 3-dimensional, non-planar structure of the glucose ring. This ring, the 6-membered pyranose ring that glucose adopts in solution and in the crystal, is not flat. It exists in a chair conformation, a specific 3-dimensional shape that is the energetically preferred geometry for 6-membered rings containing 1 oxygen atom. The chair conformation is stable because it minimizes the steric strain between the atoms attached to the ring. They can extend outward without crowding each other, each bond directed away from its neighbors with maximum efficiency. The orientation of the hydroxyl groups around the glucose ring, whether each one points axially, perpendicular to the plane of the ring, or equatorially, roughly in the plane of the ring, is fixed by the stereochemistry of the molecule, and it determines how glucose packs into the crystal lattice, which determines the lattice geometry, which determines the properties of the crystal, which determines the texture of the honey. The chain of causation from atomic orbital geometry to the feel of set honey under a thumb is entirely physical. No step in it requires anything other than the spatial preferences of electrons in shared bonds. The fructose molecules in the surrounding liquid phase have a different ring geometry. Fructose in solution adopts primarily a 5-membered furanose ring, 1 fewer atom in the ring compared to glucose's 6-membered pyranose, and this geometric difference changes the arrangement of hydroxyl groups and the overall shape of the molecule sufficiently that fructose cannot fit into the glucose monohydrate crystal lattice. This is the molecular reason for fructose's reluctance to co-crystallize with glucose. It is not a chemical incompatibility, but a geometric one. The lattice has a specific shape, and fructose does not fit that shape. So it remains in solution surrounding the glucose crystals, waiting in the liquid phase as the glucose lattice grows around and past it. In the sealed jar at ambient temperature, in the absence of any outside influence, the glucose continues its slow lattice extension, and the fructose continues its patient suspension in the liquid between the crystals. The vibration in the lattice continues at its ambient frequency. The hydrogen bonds hold their geometry. The electron distributions maintain their shape. The color deepens by degrees that are not measurable in months, only in years. The HMF rises by quantities that require careful instrumentation to detect. The aromatic compounds diminish at the upper end of their range and persist at the lower. Like everything, honey changes over time. It shifts slowly and quietly within its own chemistry, without any interference from outside. We talked about how stubbornly it holds its form, but it changes too in time, and that is completely normal. In a cool, dark room, inside a sealed jar, the only thing honey is doing is continuing the processes happening within it. It may look stable from the outside, but the real work is happening on the inside. That distinction is where the final examination begins. Inside honey, there are millions of individual connections, but they work together, hand in hand. This reminded me of the bees we talked about earlier. What happens inside the honey works on the same principle. Each part on its own is like an engine with one piece missing. It does not run. But when every part moves together at the same moment, the engine starts. Or like a bird with only one wing, it cannot fly. Honey works the same way. The glucose monohydrate crystals in a sealed vessel have been vibrating around their lattice positions for 3,000 years. The hydrogen bond network holding those crystals together has maintained its geometry for 3,000 years. The fructose in the surrounding liquid has remained in solution for 3,000 years, its furanose ring intact, its hydroxyl groups oriented in the same spatial arrangement they occupied when the vessel was sealed. The gluconic acid produced by glucose oxidase activity in the original processing is still present. Its pH it contributes to is still measurable. The electrons in the carbon-oxygen bonds of the sugar backbone are still distributed asymmetrically toward the oxygen atoms, still creating the polarity that makes these molecules interact with water in the way they always have. That vessel is in the collection of the Egyptian Museum in Cairo, and in several other institutions holding material from the New Kingdom period. It contains honey. Let us say 3,000 years have passed since the lid of that honey jar was sealed. During that time, the Egyptian pharaohs were still in power. Then the Roman Empire rose and then fell. Certain religions emerged and spread. The printing press was invented, the same one now sitting in offices everywhere, a part of daily life. America was discovered. The Second World War happened. All of this occurred within 3,000 years. During that time, approximately 120 generations of people were born, lived their lives, and came to the end of them. Not one of them opened that jar. Throughout all of it, the honey continued quietly at its own pace, making its way to the present day. It did not participate in any war. It did not build any empire. It simply stayed inside the jar, continuing its own chemistry. Its color has deepened a little. Its enzymes have diminished, but it is still honey. It simply continued, holding its lattice geometry, maintaining its acidity, keeping its glucose in crystals and its fructose in solution, proceeding through the slow chemistry of the Maillard reaction and the gradual loss of its volatile aromatics, darkening by the unavoidable degrees that 3,000 years of ambient temperature Maillard chemistry produces without requiring anything from the outside world to do so. The measurable changes in that honey, elevated HMF, diminished or absent enzymatic activity, a color that has deepened significantly from the original, are the record of those 3,000 years. They are the account the material has kept of its own duration. The HMF is not damage, it is documentation. The enzyme activity is gone, not because the honey failed, but because enzymes are proteins, and proteins denature over centuries of ambient temperature storage, even without heat. The sugar structure is intact because covalent carbon-oxygen bonds are too stable to be disrupted by time alone, and the conditions inside a sealed, dry vessel did not provide the water or the reactants that would be needed to break them. The material kept what could be kept. It released what could not be held indefinitely. The record is honest. Returning now from the atomic scale, from lattice parameters and electron distributions and quantum mechanical probability densities to the surface of the material, where the examination began. The amber that bends light at a refractive index between 1.484 and 1.504. The slight convexity at the center of an undisturbed surface. The weight that announces itself before the hand has finished lifting. These properties have not changed in their essential character across 3,000 years of honest storage. A jar of properly preserved honey opened today has the same optical behavior, the same density, the same reluctance to flow that it had when sealed. The surface is continuous with its own chemistry. The chemistry is continuous with its own history, and the history is written in the lattice and the color and the pH of the material itself. The full catalog of the 600-plus flavor compounds in honey has not yet been completed. The precise nucleation mechanism that determines which particle in which jar at which moment initiates the first glucose crystal has not been fully resolved. The relative contributions of osmotic pressure, hydrogen peroxide, and gluconic acidity to honey's preservation efficacy, each separately measurable, their combined weighting less precisely established, remain a subject of ongoing research. These are not failures of the science. They are the honest edges of what is currently known in a material that has been studied with serious attention for less than 2 centuries by instruments capable of resolving molecular structure for less than 1. 3,000 years of the material's existence, 150 years of systematic examination. The gap between those timescales is not a problem. It is simply where the interesting questions are still being formed. The pollen grains inside a jar of honey, present in quantities that vary from filtration from a few thousand to many tens of thousands per 10 grams, carry the geographic record of the landscape where the bees foraged. That record is botanical. It is specific. It identifies species, and through species identifies region, and through region identifies season and elevation and the particular configuration of flowering plants that existed within the foraging range of a particular colony in a particular year. A skilled melissopollenologist, a botanist who reads pollen, can examine a honey sample and describe the landscape that produced it with an accuracy that no other organic material quite matches. The honey carries the place it came from inside it, in physical form, sealed at the moment of processing. The bees that made this honey in Egypt with such effort flew over a landscape that no longer exists. The flowers they landed on have been replaced by other plants, desert, or buildings. It cannot be said with complete certainty, but that colony is gone. The beekeeper who collected the honey, processed it, and filled the jar is gone. The people or institution that made the jar, the root that brought that particular plant there, most likely gone. The specific human beings who sealed the wax cap with their own hands, gone for 3,000 years. The pollen inside the jar is still there. That landscape has been compressed into the grain, the chemical fingerprint, the weight of the material in a sealed jar. The honey does not know this, it simply contains it. The last quality of honey worth sitting with at the end of a long examination in the direction of its smallest structures is the one that is most difficult to state precisely without overstating it. Honey is not a symbol of anything. It is a material, a complex, measurable, chemically intricate material with specific properties that can be stated in exact values and examined with precision instruments. It preserves because of no intention, but because its chemistry happens through the combined effect of several simultaneous mechanisms to produce conditions inhospitable to the processes that cause other organic materials to decompose. It is ancient in the samples where it is found, not because it chose to persist, but because it happened to be sealed in a way that maintained the conditions its chemistry requires. There is no mystery in this that exceeds the chemistry. There is no property of honey that cannot, in principle, be fully described in molecular terms. And yet, the material that a bee spent its entire life contributing to, producing 1/12 of a teaspoon in that lifetime, the material that required the collective labor of a colony visiting 2 million flowers to produce a single pound, the material that was fanned to below 18.6% water content by bees beating their wings 200 times per second in organized, sustained shifts, this material, sealed under wax, will still be recognizable as itself in 3,000 years. Not because anyone arranged for that, because the chemistry happens to work out that way, given the right conditions, given the right container, given no interference from the outside. If one of these details stays with you, the refractive index bending light in a cool room, the lattice geometry of glucose, the pollen grain that started a crystal, the 20 degrees of temperature that separate a solid from a flow, it may be worth leaving in the comments. The quietest observations often turn out to be the most interesting ones. The honey on the shelf has not moved. The jar is still warm where a hand held it. The light through the glass is still amber. The material is still, in the practical sense, in the middle of a process it began above a field that may not exist anymore, and has, for the duration of this examination, continued. That is where it remains. We have reached the end of the video. Throughout it, we talked about what is happening inside honey and learned how everything works together. If this kind of content interests you, you can find other videos on our channel as well. See you in the next video.